Hello, let us talk about nucleophiles and electrophiles. Well, what are nucleophiles and what are electrophiles? An atom can be considered to be a nucleophile when it contains a formal negative charge or a partial negative charge, or when it has a pair of electrons that it can donate to another atom. Okay? So most of the nucleophiles that we're going to consider are atoms that have a formal charge like ethoxides. So we can consider this one to be a conjugate base of the alcohol, in this case of ethanol. We could also use ethanol because of the lone pairs of electrons on oxygen. So we could use this as a nucleophile. The double bonds can also be used because remember that when you have that that pi bond, it means that we have bonding pair of electrons. So we can use that pair of electrons to act as a nucleophile. The other one is when we have an anion or a partial anion on a carbon atom, which could be stabilized by a counter ion. So like in this case, this carbon can act as a nucleophile. For electrophiles, they will carry a formal positive charge or a partial positive charge, and they are deficient in electrons, so they should be able to accept a pair of electrons. Most of the ones that we are going to use is when we have a carbon connected to more electronegative atom. So this more electronegative atom is withdrawing electrons from the carbon, making that carbon deficient. So it becomes an electrophile. Others are those that are positively charged. So we call this a carbocation. So we are going to use these ones also as electrophiles. Identify the atom labeled in red as a nucleophile, electrophile, or neither. Starting from A, we already mentioned that when we have this bond, it simply means that we have a bonding pair of electrons. So this is going to be a nucleophile. We did not say anything about a carbon that's not bonded to an electronegative atom, so this is neither. This is a nucleophile because of the lone pairs on oxygen. This is going to be electrophile because the bromine here is more electronegative, so therefore the carbon here is going to be more electropositive and deficient in electrons. This is going to be a nucleophile, this is going to be a nucleophile, this is going to be an electrophile, and this one is going to be a nucleophile. Now let us go into reaction mechanisms and how we do the arrow pushing. In every reaction, you need to be able to identify the main steps for the movement of electrons. These 4 steps include what we call the nucleophilic attack. So we need to identify the nucleophile. The nucleophile will usually attack an electrophile. We need to identify a method as being a loss of a leaving group. We need to identify a proton transfer where there's an acid-base reaction. Then we also need to identify a mechanism as being a rearrangement. So these 4 steps are very important because they are going to form the basis of our reaction mechanisms that we are going to use from now onwards. How do we represent that in a mechanistic step? Okay, so in the first step here, we have a proton transfer because we have lone pairs on oxygen, so oxygen is donating electrons to the hydrogen. So this oxygen is acting, this compound is acting as a base, which we can classify as a Lewis base. It has lone pairs of electrons that is donating. The HBr is accepting the electrons, it's acting as a Lewis. This reagent is acting as a Lewis acid. So we call that a proton transfer. So in a proton transfer, there is an acid-base reaction. Once that one is formed, once that one happens, we form protonated alcohol, which can be kicked out as a leaving group because it leaves as water, which is neutral. So we consider that a loss of leaving group. So loss of leaving group usually involves the kicking out of a compound that is going to be stable. Only compounds that can be kicked out as stable molecules will be removed as leaving groups. In the next steps, once that happens, we form a carbocation at this position. So this is called a secondary. That's a secondary carbon because this carbon is bonded to one carbon here and another carbon over there. So we call this position secondary. So when you have a secondary carbocation, and if there's a possibility of forming a tertiary, because this carbon here is bonded to 1, 2, and 3, bonded to 3 other carbons, so we call it tertiary position. So if there's a possibility of transforming a secondary carbocation to a tertiary carbocation, then that rearrangement is going to occur because tertiary carbocations are more stable than secondary carbocations. And then after that we can have a nucleophilic attack. So here, this bromine has lone pairs of electrons, so it's going to attack the nucleophile. Then we end up with the product. So every step in a reaction mechanism, we need to be able to identify and classify it as being any of those 4. In some cases, we might have a concerted mechanism. Now, what is a concerted mechanism? In a concerted mechanism, we might have more arrow pushings, not just one arrow pushing, more arrow pushings in one step. So it may include more than one of these main steps that we talked about. Let us look at this example. So here we have a nucleophilic attack because the hydroxyl group is acting as a nucleophile using those lone pairs to attack the electrophile. Then there is the loss of leaving group, LLG, loss of leaving group, nucleophilic attack, loss of leaving group. So we have 2 steps taking place at the same time. We call that a concerted mechanism. Okay? Now, we just mentioned about the carbocation rearrangement. What are the things to consider for a carbocation rearrangement, or under which conditions would you be expected to perform a carbocation rearrangement? Now, usually we don't form carbocations from methyl groups. We avoid forming carbocations for primary groups, but if there is a carbocation for a secondary group, we can have a rearrangement to form a tertiary. So most of the reactions we are going to consider, we are going to realize rearrangements from secondary to tertiary, and in most cases, almost over 90% of the time, we are not going to consider primary carbocations because they are not stable. Alright? So let us look at an example here. So this is secondary position, this is tertiary position. So this carbon here is bonded to 3 others. So if there's a carbocation in secondary position, we can have a rearrangement. So the hydrogen moves to the next carbon, so we call that a hydride shift. So we can sometimes have a hydride shift, or we can have a methyl shift. If there's no hydrogen, so like in this case we have a methyl group, there's no hydrogen, but this secondary position is not stable, so then we need to transform this quaternary position to tertiary, because the tertiary carbocation is going to be more stable. Okay, so we are going to do what is called a methyl shift. So we move that methyl group to that second carbon, the adjacent one, and then we end up with a tertiary carbocation which is more stable. So we are going to be using the terms hydride shift and methyl shift. They usually occur from adjacent carbon atoms. Okay? Now identify the pattern of each sequence of arrow pushing as nucleophilic attack, proton transfer, loss of leaving group, rearrangement, or a combination of concerted type of reactions. So we need to be able to classify the atoms involved either as nucleophiles or electrophiles. Very important. So let us start with this. This oxygen is acting as a nucleophile because it has lone pairs of electrons. It can attack this carbonyl. So this carbonyl is deficient in electrons, and then we can also have resonance structure because it is connected to oxygen, which is more electronegative. So it's going to attack that position, so we call that a nucleophilic attack. Okay? Remember, we cannot have 5 bonds originating from carbon, so then there's going to be a reorganization. So this is nucleophilic attack. And then what happens next is we have these electrons coming back there, and then it kicks out the chlorine as chloride ion. So we can consider this step as being loss of a leaving group. So the whole of this process is nucleophilic attack. The whole of this process is loss of a leaving group. And let us look at what happens next. So next we have water acting as a nucleophile, but it is taking a proton. Because it's taking a proton, that means we have an acid-base reaction. So for acid-base reaction, we call that a proton transfer. So in this reaction, we have 3 main steps: nucleophilic attack, loss of leaving group, and proton transfer.